In this video, we will discuss the Baeyer-Villiger reaction and some qualitative tests for aldehydes and ketones. The Baeyer-Villiger reaction is an oxidation reaction where an aldehyde or a ketone is reacted with a peroxycarboxylic acid, which is what this structure is here. An example of which would be MCPBA, which is one that you learned earlier in OCHEM 2 and possibly the end of OCHEM 1 that allowed us to turn an alkene into an epoxide. It is also a peroxycarboxylic acid and can be used in the Baeyer-Villiger reaction. So you react an aldehyde or a ketone with a peroxycarboxylic acid, and you end up inserting an oxygen between the carbonyl carbon and one of the alkyl groups, or in between the oxygen and a hydrogen in the case of an aldehyde. And this will result in the formation of an ester from a ketone or a carboxylic acid from an aldehyde. So the big question here is, how does this work? To understand how this reaction works, we're going to take a look at the mechanism. In this mechanism, the letter M is going to stand for the migrating group. This is going to be the indicator of which group is going to be migrating to the oxygen. So we know that ultimately we're going to insert an oxygen between the carbonyl carbon and the migrating group. I'm never going to ask you to reproduce this mechanism, but you do need to be able to recognize the steps and understand how it works so that you can predict the product correctly. So in our first step, since we were in acidic conditions, the ketone or aldehyde is protonated on the carbonyl oxygen. The compound then undergoes a nucleophilic addition to the carbonyl from the outermost oxygen of the peroxycarboxylic acid. And then we will push the electrons in the carbonyl pi bond up onto the positively charged oxygen of the carbonyl. So now we have a positive charge on the oxygen in the peroxycarboxylic acid. At this point, the conjugate base of our acid can deprotonate this. And then we will have another protonation of the carbonyl oxygen in the peroxycarboxylic acid. Now this is the point where the really fun stuff happens. So our conjugate base, is going to deprotonate our original carbonyl oxygen, and the electrons in this bond are going to come down to form a pi bond between that oxygen and what used to be the carbonyl carbon. Now when it does this, that is going to push the migrating group onto the oxygen. And then this bond between the two oxygens is going to break to form a pi bond between the oxygen and the carbonyl carbon, which pushes these pi electrons onto the protonated oxygen. Which results in the formation of an ester and a carboxylic acid from the peroxycarboxylic acid. Now, taking a look at this pretty crazy mechanistic step here, we can look at kind of some bond strengths in order to understand what happened here. So having two oxygens directly attached to one carbon is not usually a stable situation. So that's going to encourage the breaking of the bond between the carbonyl carbon and the oxygen. So instead what we do is we migrate the migrating group onto the oxygen, which gets rid of one bond here. And then the bond between the two oxygens is a weak bond. This is a peroxy bond. Having a bond between these two electronegative atoms is not going to be preferred. So that bond is going to break to form a pi bond between an oxygen and a carbon, which is a much more preferred bond. So how do we know which group needs to be moved when we're looking at an aldehyde or a ketone? This comes down to the migratory aptitude, which is essentially how easily a group is migrated. Our migratory aptitude is that hydrogen moves more easily, and that's just simply because it is a tiny atom and it's easy to move it, than a phenyl, which is more likely to migrate than a tertiary alkyl, which is more likely to move than a secondary, which has a greater migratory aptitude than primary, and so forth. So most of this comes down to the stabilization provided by hyperconjugation and electron donation of more alkyl groups. But the hydrogen kind of stands out from that just because its size allows it to move easily. So if we look at these examples here, we can practice this. So go ahead and pause and try to determine where the oxygen will be inserted in each of these reactions. In the first problem, we have a ketone and it's cyclic. So our question is the oxygen going to be inserted here or here? In order to answer that question, we look at the substitution of each of these carbons. This carbon is tertiary, this one is secondary, which means the oxygen is going to be inserted between the carbonyl carbon and the tertiary carbon. So we are going to end up making a 6-membered ring. Don't forget about your methyl group. And we have an ester. In the next problem, we have an aldehyde. Anytime you're doing this reaction with an aldehyde, you're going to end up putting the oxygen between the carbonyl carbon and the hydrogen. And this is simply because the hydrogen has the greatest migratory aptitude. So our product here is going to be acetic acid. And then in our last one, we have to compare a secondary carbon to a phenyl group. A phenyl group has a greater migratory aptitude, so we know that we're going to insert here. Which results in this ester. Now, the way that I drew these out, the oxygen ended up being inserted on the right-hand side every time, but that's not necessarily going to be the case. And in the last bit of chapter 16, we're going to discuss some qualitative tests for aldehydes and ketones. So these tests are considered qualitative because each of these reactions creates a distinct and observable product. So we're looking for color change or formation of a precipitate. In the first reaction, we have an aldehyde or a ketone reacting with 2,4-dinitrophenylhydrazine. Now this is a dye that when reacted with an aldehyde or a ketone produces a hydrazone, which is an orange precipitate. So a 2,4-dinitrophenylhydrazine hydrazone is going to give us an orange precipitate. In the next reaction, we have an aldehyde or a ketone reacting with hydroxylamine, and this is going to give us an oxime. And oximes are traditionally white precipitates. And in our last one, you can react an aldehyde with silver 1-diamine in water, and this is actually going to give us a carboxylate plus silver metal, which will precipitate out and create a mirrored surface across the top of the solution, and will also possibly plate silver onto whatever glass container you're doing the reaction in. This is called the Tollens test. and this is a test for aldehydes. So this one really is very cool because it uses a very similar process to the technique for making an antique mirror from a piece of glass. That uses something like Windex or commercial ammonia and a silver salt, and you're able to precipitate silver onto the surface and create a mirror. So all of these will indicate the presence of an aldehyde or a ketone, except the Tollens test, which only works with aldehydes. So if you are working in a lab and you run a reaction and you think you may have formed a ketone, you can test that out by adding in 2,4-dinitrophenylhydrazine. If an orange precipitate forms, then you know that you created a ketone. So this is just a qualitative test.